Okay, we are on page 2 now. So page 2 we have problem number 4 and number 5. It's asking us to, Professor Solomon is asking us to look at different acid and base and see which one is the better one, a stronger one. And it's asking us not to look at the pKa, just look at the structure, by the structure. Typically when I'm doing this, I like to look at the conjugate base of those potential acids. To me, if the conjugate base is better, more stable, the acid is stronger. Because remember, if I write something here, we have an acid, right? And this acid is going to make a conjugated base. Now, if the conjugate base is stable, and once it formed is stable, it's going to affect the acid. So the acid would be also stronger. So if we can compare the conjugate bases to each other, that is going to help us with the acid. So that's what I did here. So I look at the conjugate base for the first one. We selected the cyclohexane. The cyclohexane, which is not an aromatic compound, A, so I call A here. So the conjugate base for A, remember this is not a benzene, it's a cyclohexane, would be this. So the conjugate base for this would be this oxygen. And we have a nitro group here next to it. Conjugate base for B is this one. So this we have, the H is gone, so we have O minus. Then we have conjugate base for the CF3, which is C. Then we have conjugate base for the E. So now the O is here, O minus is here. Then we have the conjugate base for D. Did I have it right? No, I'm sorry. This is E, and this is D. Okay. So then that's O minus. Very similar to this. So let's go look at the influence that those groups have on the O minus for all of these. The first one is nitro group. Nitro group we're going to learn is very strong withdrawing group. That means it's going to take electron away from the oxygen. It helps the oxygen not to carry fully negative charge. So this is the strongest and the most stable base. The next one would be the methoxy group. So this is what we call a methoxy group. Methoxy group is also electron withdrawing. So we draw electron from the oxygen and it helps with this oxygen. So the A makes this base, conjugated base, very stable. Then we look at the CF3. CF3 is also electron withdrawing group, but not as good as OCH3. We're going to learn these are called resonance structure, resonance effect, resonance, and these are called inductive effect. So resonance is a little bit better than inductive. Then we have the D and E. So these are both of them O minus. They're both O minus. So the effect of the CF3 is not as strong. So we're going to have the benzoic acid, conjugate base of the benzoic acid, here a little bit more stable than trifluorobenzoic acid. So the order would be now, again, cyclohexane, methoxy, CF3, benzene group and CF3 for these are the two attached as a not directly to the benzene group, but attached as a okay. So in problem number 5, they're asking us to look at two acids together versus the previous problem we had many more. So if you look at the phenols, this is all phenols here. So you have a phenol, we have a phenol, and then at the position 4, we have a methyl group, and we have a CF3 group. I wrote on it, and sorry, it's a fluorine group. So we are going to look at again conjugate base for these two acids. So the conjugate base for the methyl group, so we're going to look at the O minus here, and see what effect that fluorine has or methyl group has. So they have opposite effect actually. Fluorine is an electron withdrawing group. Methyl group is an electron releasing group. Withdrawing, releasing. So withdrawing is going to help with the O minus a lot more than methyl group. So I would predict that the fluorosubstituted phenol is going to be a lot more acidic than the methyl group. And I think if you check the pKa, you see that is correct. The next one again are two phenols. So you have this phenol, we have this phenol, and we have two groups. We have a methyl group and we have a nitro group. Nitro group is again electron withdrawing. I'm sorry. Yeah, I said the right thing. Electron withdrawing group. So it helps. So this electron withdrawing group, I drew it twice, is going to help with the O minus. So this would be a better, so this one would be a better conjugated base, more stable. If this was a methyl group, I didn't draw that. So because of that, this nitro group on the phenol makes this a little bit more acidic, a stronger acid than methyl group. So I draw the arrow this way. The next one, again, two phenols, but the nitro group, I didn't draw it here. The nitro group, one of them is in position 4. This is in position 3. We're going to learn that position 4, which we call a para position, by resonance structure has more influence than position 3, which we call a metal position. Because of that, when we have a para position for the phenol, makes this phenol more acidic than when the nitro group is on the metal position. Again, then we have to draw the resonance structure to prove that. So the next one is sort of obvious and not obvious. We know phenols in general a lot more acidic than the alcohol. Alcohol are not really acidic at all. So if you look at this is a phenol, this is an alcohol. So always phenol would be more acidic than alcohol. And part of it is this O minus as a conjugated base has a resonance structure, which this one does not have a resonance structure. Then we're going to compare two electron withdrawing group, F and a bromine, attack and influence they have on the phenols. So the phenol would be a lot more influenced by the fluorine than the bromine, makes this O minus as a conjugate base a lot more stable than the bromine. So because of that, the acid that you can make from the fluoro compound, 4-fluorophenol, is a lot more acidic than the bromine, a bromo compound, and we can look at that as a pKa later on and make sure that what we're predicting is correct.